Swayam Prabha. Digital India. Educated India.
If we have some other quantity which are AC is a time dependent quantity, right? Time dependent quantity. So it is basically, suppose this is the quantity. So if you represent this, you see the polarity will keep changing. This is a sinusoidal variation, right? Okay. This peak value is basically touching here. It is going this way. Peak value is 10 pm. The voltage, this is time. So here in this case, T is the instant at which the voltage is following this particular function, which is AC. So it is basically a time. Omega is angular frequency. The Vm is peak magnitude of a C signal. Okay, the peak magnitude of AC signal, and this Vt, which is a function of time, is an instantaneous voltage. Suppose you want to have the voltage at this T1. So what is the voltage at this T1? This is the voltage. This is V at T1. Similarly, you want to have something at 2. So the quantity which is, this is nothing but Vt2 corresponding to T2. Similarly, the instantaneous at which the voltage is defined is varying and is a function of time. So it is a time dependent quantity, and it is having the variation in the polarity in each cycle. So one cycle is basically after which it is repeats. So we'll be talking about in detail in the case of AC circuit whenever we will be starting this in coming lectures. So for time being, you assume that this is T and omega is the angular frequency which is defined by 2 pi by T. So just remember that, otherwise we'll again have a look into this, what does it mean and how this is being written in this particular format. So this is the AC quantities, and AC quantities are represented as small letters, small case letters. Okay. So for example, P is a AC voltage, small I AC current, small p AC power or the instantaneous power. Okay, so this is something which we will be looking into, the variation of different parameters or quantities based upon the time. And now let us consider the DC source. Okay, so we'll be starting the source. So source is nothing but the electrical element. Electrical element which is a part of a circuit. So if we talk about source, specifically the DC, then we can think of from the previous discussion that it is a source which is constant. So source can be a voltage source or a current source. Okay, source can be a voltage or current source. So when we talk about the constant voltage, it means that it is not depending upon the time, isn't it? So this is the ideal voltage. So this is the voltage, and this is the magnitude of quantity, and this is the time. This is basically a constant. This is voltage. And if it is a current, then same thing will happen to current, constant. This is basically the current. The constant current means, so whenever we talk about the DC source which is ideal, so now we'll just define something very non-feasible or practically impossible thing, but we can assume as a part of the circuit, which is ideal voltage source. So what is the ideal voltage source? It means that the voltage magnitude is independent of time and presence of other element. In the circuit. Okay, so this line is very important. Why? Because it is saying that the magnitude is independent of time and presence of any other element of the circuit. So basically we are having an idea of dependent and independent source. Okay, so for time being, let us assume the voltage source we are talking about. We'll just use the term voltage, independent voltage source and the dependent okay. So if it is independent voltage source, we have already seen that it is independent of time and presence of circuit element. So the value or the magnitude will not depend on time, which we have seen already. And the important part is the representation. So that it is represented in the circuit as either this way, or so this is normally for the battery, and this is also for the constant DC source, and this is a polarity. So bigger line towards connection in the circuit is now considered as positive, and smaller line or connected to another part of circuit between terminal A and B can A and B. So the voltage is V, the voltage is V. So this is the representation of, or either this way or this way, it is represented as independent voltage source. And whenever any source is represented in a diamond shape, this way, it means that this is a dependent source. Okay. And when, if we go a little back, here we have seen AC quantity, right, in which the polarity is changing. Similarly, in case of DC, the polarity is not changing because it's a constant, and therefore if we talk about the independent voltage source of type AC, then it is represented by this. This VT, small case VT is the AC. This is for DC. This is for DC because the polarity is given. So DC dependent source. Now the current source. The current source is basically the representation in the circuit will be seen very frequently in this way, which is depending upon the current of the circuit which is flowing in the particular direction. So if it is on the top, it means that current is flowing this way in the circuit, and if this is represented by this down arrow, it means that current is flowing this way. A, B, A prime, B prime. So in any circuit, if you see some arrow, it means it is a current source, and if it is represented in the circular this circle, so it shows it is a independent source. And again, if something which is represented as in some diamond shape or this form, or depending upon the flow of the current, if it is represented in sorry, in this particular form, okay, then it is a dependent source or dependent current source. So this is how it is represented. Now in the circuit, if you see, the dependency of these voltage can be in any term. So if you talk about the dependent source, right? So let us list down the dependent source. What type of dependent source can be there in the electrical circuit? So dependent sources. I'll draw some of the circuit. Let us consider these 4 cases. So this basically represents a current source. If the amount of current source is 3 V naught, then consider one more circuit. It's again a current source. What type? Dependent, correct? And the magnitude of the current which is flowing is 3 I naught. Okay. Now what do you think? Both are the current source, but they are depending upon what? The magnitude depending upon the different quantity which is a part of the other circuit element. So V naught, which can be another circuit element quantity, and the voltage is taken as the dependent parameter for this current source. So this will be known as the A. This is B. Okay. So what is the A can be named as? Basically, it's the dependent current source. So voltage dependent, not dependent, we can say controlled, because the magnitude is controlled by the voltage is flowing. So voltage controlled current source. Okay. So voltage controlled current. In short, we can write as voltage controlled current source. Then what about the B? B is basically the current source which is controlled by a current of the another element, which is I naught. So it can be another circuit is connected to between these two terminals. So some current I naught of the other element. So this can be written as current controlled current source. Current controlled current source. In the short, CCCS. Now consider another case where you have this representation, and the voltage is again suppose 3 V naught, and this V naught is some other element quantity, and another representation of this consider as C, this as D. So this is also dependent voltage source, but magnitude depending upon some other element. So similarly, can you write the name of the C? This is a dependent voltage source controlled by the voltage. So it is a voltage controlled voltage source, right? So voltage controlled voltage source. And similarly for the D we can easily write what? The voltage controlled or current controlled? The magnitude is dependent upon the I naught, right? So we can write that current controlled voltage. So basically current controlled voltage. These are the four types of different dependent sources which will be very frequently seen in the electric circuits. So do not get confused. I will see some of the examples. So we want to draw, now come back to the ideal sources. As we have seen, it does not depend upon any of the voltage. So ideal source okay, the quantity does not change regardless of the voltage across its terminal. So if we say something like voltage across the terminal, what does it mean, voltage across the terminal of a current source? Does it make any sense? Voltage across the terminal of current source, how much voltage across the terminal can be? So when it is the ideal source, the magnitude of current source is independent of the voltage. So whatever the voltage may be, magnitude of current source is independent of voltage across this source. Similarly, ideal voltage source, the magnitude of voltage is independent of the current drawn by the. So when we talk about the ideal voltage source or ideal current source, whatever the type of waveform or the current you can draw from the source, and the voltage should not change in the voltage source. Similarly, whatever amount of current we want to draw, we can draw irrespective of the voltage across this current source terminal. So we have seen the ideal voltage and the ideal current source. So let us recall, in general, ideal source, okay, either voltage or current, the magnitude is independent of time. Correct? The magnitude of the source is independent of time in case of ideal source. So suppose we want to draw the characteristic. So this is your time and this is your voltage. So in ideal voltage source, with time there is no variation. Okay, so this is constant. Similarly, ideal current source, if you want to draw the characteristic, so this is again time and this is current I, this is a DC current which is nothing but the constant. So there is no variation with respect to time. And now you have a IV characteristic of a ideal voltage source. So this is VT, this is IT, this is V and I. So ideal voltage, why this is I is written this way, it can be a function of time also. So the voltage will be constant. Now similarly, if we have here, suppose I and voltage is a variable, now ideal current source will be this. So this is the characteristic of basically the current IV. So this is IV characteristic. Of ideal voltage source. And this is ideal voltage, sorry, this is ideal current source, right? So this is nothing but the ideal current source, and this is ideal voltage source. So these are the ideal source conditions. So practically, if you talk about, there is no ideal source, but for the analysis purpose, we can always assume that the given battery is not losing its voltage irrespective of the current drawn from its terminal. So with this we'll define some linearity. So we know that the linearity is something when, okay, let us define first. So a function is said to be linear if it holds the following condition, right? Hold the following condition. What is that condition? Nothing but a times of f of x1 plus b time of. So this is the main condition for a linearity to be checked. So most of the circuit in our case will be linear. So before going into that detail, let us define the resistance. We'll come back to the linearity. So what is the resistance? What is the resistance? Resistance is a property of a material. Property of a material which opposes the flow of current or charge. Flow of charge is nothing but the current. Okay. So the material of property, by virtue of it, it opposes the flow of charge within the bulb. So when we talk about the resistance, so suppose a conductor which is having a length L, okay, this is a conductor of length L or any element, and the cross section area is A. So the resistance is mathematically defined as rho L by A. So resistance is represented by R. So R is proportional to the length, which is the length of the conductor, and R is inversely proportional to the area of the cross section, and rho here is the resistivity of the material. Which is a material property. Okay, so just make it a little bit. So if the resistance we want to compute, we should know the material property, which is resistivity. So for good conductors, conductor of electricity, the value of rho is very low. Okay, so for example, if we see metals, suppose copper, silver. Okay, this lies in the range of 8 ohm meter. So the resistance is measured in ohm, represented by omega. So the unit of resistivity from here you can compute that L is in meters, this will be in meter square, so this is per meter, so rho goes to ohm and meter, so which is the unit here which is mentioned, ohm meter. And the one more property which is conductance, so it is inverse of resistance, which is represented by G. Okay, is represented by G, and G is nothing but 1 by R, and the measurement quantity, measurement unit is ohm inverse or mho, inverse omega or mho. It is also denoted as Siemens, which is represented by capital S. Okay, so this is the conductance. So for metals or good conductors, the conductance should be as high as possible. So basically the formal definition is conductance is the ease or ability to ease, right? Ability to conduct the electric current through a material. So this is basically the ability to conduct the electric current through a material. So whenever the conductance is high, it means that the conductor is a good, or the material is a good conductor, in fact. Okay, the material is a good conductor. So let us define now the Ohm's law. Okay, so we have seen the resistance where it is mentioned at R equal to rho L by A. Now suppose one of the very important law, which is Ohm's law. Okay, so Ohm's law is very important and fundamental law which is defined empirically, and it states that, so first we'll write the definition or what it states. So it states that at given temperature, the voltage V across the resistor is directly proportional to the amount of current flowing through it. So suppose there is a resistor. Okay, the resistor is represented by a zigzag line. So resistor R, the current is flowing in this direction, the voltage drop is this way. So the voltage drop is proportional to the current I. So in general term, where it can be a function of time. So for time being, it is defined at the constant of proportionality is resistance R. So the resistance is a material property which can change if the internal or external conditions of elements are altered. So if we have put the proportionality constant R times of I, this is the basically Ohm's law. No, sorry, this will be, because after putting the proportionality constant, this will be equal to I. So V equal to IR. Now going back to the units, so here again the V is basically the voltage across the resistor, and now the 1 ohm, if you want to define 1 ohm, is nothing but the 1 volt per ampere from here. Okay, so it means that to apply 1 volt, and if it appears as a flow of current of 1 ampere, then it is said to be a 1 ohm resistance provided by the material. Okay, now consider a circuit. So it is said that the system condition should not be altered. I mean, R is a proportionality constant and R should be independent of variation. So that's why it is written at a given temperature, because R can be a function of temperature, time, or any condition of the circuit in which it can be dependent. So in general, we'll be considering it as an independent of temperature, or throughout the circuit theory, the temperature variation of the element can be neglected for solving the circuit. So this is the IR characteristic, I and V, IV characteristic, and the slope is given as R. Okay, but this is a linear resistor. This circuit is linear, where V is proportional to I, and it is linear circuit. Normally the practical, if we find, it will be some non-linear behavior. So the resistance will keep on changing. The resistance, the slope is here is different, and the slope here is different. So R is here R1, and here is R double prime. So the slope keeps changing, and it turns to be non-linear. Okay, and it turns to be non-linear circuit. Now if we have, so we have seen the linear and non-linear circuit. So suppose, for example, will be taking a very small example. Okay, so the electric iron, suppose an electric iron draws a current 2 ampere from a source rated to 220 volt. So find its resistance. Now there is a trick in this question. We can directly find, okay, V is equal to IR. Okay, so R is nothing but V by I. 220 divided by 2, 110 ohms. So this is the answer. We could find out using Ohm's law very easily, but the assumption is with temperature. Iron can go up to a very high temperature, but R is given, which is not a function of temperature because we have not been provided the coefficient of temperature variation. So how much the dependency of resistance is happening on the temperature is not provided. So for that case, assuming R to be independent of temperature. Okay. Now if we see some circuit, for example, now you consider this following circuit. Okay, a very simple circuit where you have a 3 resistors R1, R2, R3, and the voltage is V, which is applied here. So assuming the direction of the current flow this, in this and this. So let us define what is the node, what is the branch, and what is the loop. Okay, so one by one we'll see what this definition means, because we'll be needing it for the analysis of the circuit when it will come to applying different theorems in different type of circuit. So keeping that in mind, okay, let us go a little up so that we can see the circuit. So let us define first branch. What do you mean by branch? So in any electrical circuit, the different elements, here suppose resistance is there, so different component of these circuit R1, R2, R3 will be connected in a different fashion, and this different arrangement of the circuit which is being used, okay, in the circuit. So we may regard a network as an interconnection, as I said, whereas a circuit of the network providing one or more closed paths. So those closed paths is known as the loops. So suppose we name it A, this point is B, then this is N. Okay, so starting from N, so we can write loops. What the loop can be? N, A, B, N. So N, A, B, and the another loop can be, suppose here is C. So N, B, C, N, or a bigger one, N, A, B, C, N. Okay, so these are the loops, but loops are also can be dependent or independent. So the loops where we cannot have a smallest loop is known as mesh. Okay, so the loop can be big, small, containing a multiple smaller loop inside, but the smallest loop is mesh. So we have one mesh A, B, N, A, and the another one is N, B, C, N, so which is known as the independent loops. Now the branch is basically representing a single element, so it can be, so branch is basically, it represents a single element which can be a voltage source, or a resistor, or any other element. So any element which is connected between 2 points represents a branch, and it is suppose denoted by B. Okay, now nodes. When two or more than two branches are connected at same point, connected at the same point, then that point becomes a node. So suppose one branch AB is connected on the B, then B and N is there. So this is a branch or not? Is BC a branch? So question first, is BC a branch? First look at the definition. This is a question. First look at the definition of branch. What it is? It is basically a element. So do you think any element is connected between B and C? It is just a conducting conductor which is a contact and represented at the same voltage, right? It is elevated to the same voltage and there is no element in this section. So BC is not a branch. BC is not a branch. Okay, so keep this in mind. BC is not a branch. So when two or more than two branches are connected at the same point, then the point is known as node. Then the point is known as node, represented by N, and the loop suppose is represented by L. So we have a very beautiful equation to correlate that. Okay, total number of branches is nothing but the number of independent loops or fundamental loop plus nodes minus 1. Now how we'll recognize this? So total number of loops, how many total loops are there in this? So now here in this case, number of nodes are 3. Which one? A, B and N. And then number of independent loops, 2. Independent loops. So number of branch will be 3 plus 2 minus 1, which is 4. So which are the branch? AN, AB, BN, CN. Because BC is not a branch, there is no element connected. So here no element is there, so it is not a branch.